Okay, so yeah, this is my second time coming here. So I attended Phil's talk last time, and I decided, you know what, I'm going to give presenting a try. Potentially this was slightly too early because I told Phil that I was going to be ready to do this about a week and a half ago, and that is very pressed for time for slides. So hopefully it's coherent enough to have something interesting to share. So this talk was initially inspired based on Phil's talk, This Is Not Your Grandparents' C++, where he goes over C++ throughout time and how it's evolved to respond to new pressures. And his title is quite interesting because it alludes to the story of the car manufacturer Oldsmobile, who had a famous ad in the 80s for "This is not your father's Oldsmobile," because they were struggling with pressure from competitors and they were seen as an old-fashioned brand, and they were trying to modernize and advertise to the youth. And Phil draws some parallels to this similar sensation around C++. But hopefully C++ did it before with C++ 11 modernizing, and potentially and hopefully it survives again. But this question really does bring, or this sentiment does also beg another question. If C++ is having an Oldsmobile moment, then what is the competition doing? And obviously, you've seen the talk title. This is going to be focusing specific, and you can't avoid it at the moment. So this is going to be focusing on the funny crab language. Technically, that is the Crablang mascot, not the Rust mascot Ferris, but I feel like that stands out. That is a reasonable picture. But I'm not going to be focusing on safety and the borrow checker. They take too much airtime for C++ discussion or Rust discussions, and often I feel like people get the impression that you go to Rust, you sacrifice everything nice from C++, and then you gain safety. And in a lot of industries, that's just not a great trade-off, or that's not that appealing, and people aren't interested in that. And so I want to go through some comparison and some introduction to Rust this ended up being. So what is C++? C++ is a C-inspired systems language that uses primarily RAI for memory management, at least in modern C++. It's an object-oriented language relying on encapsulation and inheritance. It's got a heavy focus on zero-cost abstractions. It uses value semantics. It provides access to C for getting low-level control, and then it releases on a 3-year cadence. On the other hand, what's Rust? Rust is very heavily C++ inspired and has learned a lot of lessons from C++. And also it's got a lot of OCaml inspiration. It also uses RAI for memory management. Generally, Rust code is fairly object-oriented, although it doesn't have inheritance, so sometimes the style is a bit different. It focuses heavily on low-cost abstractions, but not necessarily fully zero-cost, but zero-cost where possible. It has value semantics, the same as C++, and then it provides escape hatches such as unsafe for low-level optimizations and accessing FFI and other system resources, and it's got a 6-week release cadence. So a quick introduction, since how many people here have actually started learning Rust or taken a look into Rust? Okay, right. Somewhere between a third and a half. So a quick introduction to Rust syntax. It mostly doesn't look, I feel like it doesn't look too different to C++ generally, but people seem to think it's weird. But the biggest difference is, one of the big differences is that for variable declarations, you don't have, instead of having the type name followed by the identifier name, you have the identifier name colon the type name. So this declares a variable mynum with a value of 9, and it prints the sum is the value name. Println there should be familiar to people that are up to speed with C++, since C++ 23 added very similar syntax. The exclamation mark, it's technically not a function here, it's a macro, but it looks like a function. So you can declare a function using the fn keyword, and then you take your argument list, again, identifier name, colon, type name, for your arguments, and then the arrow with the return type, which looks a lot like C++'s auto returns. And then assign the result and return it. But actually in Rust, the last expression in a statement list is its value and statements return values. So in this case, you can drop the return and just return result. Calling this function, we can do it basically the same way you would expect in C++, but note now we have an angry red squiggle. And that is because in Rust, the default is that variables are immutable. And as the compiler kindly suggests, consider making this binding mutable on line 7. So doing that, it now works and prints 19 as we would expect. Another thing, in C++ we have auto for type inference. In Rust, because of the different order, you can quite often just omit the type entirely. And also the variable result here is relatively redundant because that's the only thing the function is doing. So you can just return first plus second. Going into pointers, I was going to have a long spiel. This is stolen content from Phil. So pointers, hopefully most of this audience is familiar with C++ pointers versus references. So references you can't rebind, and you cannot address references, and they can't be null. In Rust, Rust also primarily uses references, but they're fairly different to C++ references. And also so we have the const reference, which is just %t, and we have mutable references, which are %mut t. And generally in Rust, the way I find it easiest to think about them is that they are non-null pointers to a validly constructed t. So in C++, you probably shouldn't have your references dangling, but you can. In Rust, if your reference is dangling, that's generally considered to be undefined behavior. And to get there, you have to have gone through some sort of unsafe. The other big one here is the aliasable column row. If people are familiar with the restrict keyword in C++, or not C++, it's not a C++ keyword. The restrict keyword in C, which a lot of C++ compilers support, it basically means can you have 2 pointers to the same section of memory at the same time? And you can only do that in Rust for non-mutable references. So that is the big one that the borrow checker does. Rust also has pointers, which if you're using unsafe code, you can use. And they're very similar to C++ pointers, apart from to do basically anything useful with them, you need to convert them to a reference first. Data types wise, C++ has very rich classes and structs. It has enums and it has unions. In Rust, we have structs, which are much closer to C structs. They don't have any methods, they don't have constructors. We have enums, which they do share the duty of C++ enums, but they're generally more like stood variant, so they are a tagged union. And it does have unions, but generally they're only used for interfacing with C code that is also using unions. So as an example of a Rust struct, you can have an access modifier at the start. So can it be used outside of the current module? And then you have the keyword struct, the type name, and then again you have the identifier name : type name sequence rather than the C-style type name identifier name. And each of those can also have access modifiers for are they visible outside of the current module. Some syntax for using structs is that we only have initializer init statements. So more like in C, we don't have constructors in Rust. So here I have a program, a function that assigns a value to UUID, a value to health, and then constructs a person by setting its ID and health internally. And then to access the fields within a struct, you just use a dot syntax like you would expect from C++. There is a blue squiggle under health, and that is because if the type name or if the variable you're assigning to the field has the same name as the field, if you just put that name, it will infer that that is the variable you're wanting to use. And also you can obviously use constants, so I got rid of UUID on this slide as well. Okay, so if we've got structs, how do we do objects? I said Rust is object-oriented generally. So stealing more stuff from Phil, his example class. Hopefully to people that are familiar with C++, there is some things in here that people are screaming about for performance reasons that will become evident. So to start, probably expectedly, the member variables, we just create a struct to hold the member variables. Rust has generics very similar to the syntax, with similar syntax to C++. So the vec _ string is just a vector of strings. And then we have a string name as well. And then for creating the fields, and then for the constructor, we have this weird impl block in Rust that tells us that we're implementing methods again that are associated with the struct. And by convention in Rust, we have a function new for the constructor that takes in arguments and then returns by value our object. So rather than in C++ where we have a constructor. So here we have a function that takes in a reference to the string name, a reference to a vector of strings data, and then assigns name by clone, and then data by clone, which C++ just implicitly clones your string and clones your vector and all of the strings within your vector, which to an experienced C++ person, they're aware of this, but especially for beginners, that is a huge performance hole that a lot of people fall into. And Rust makes that explicit. Another thing to quickly note, because I do this on slides, is that within an impl block and within traits that I'm going to get to later, the identifier, the type self with a capital S is an alias of the type being implemented. So we can also do new return self. And in this case, because it's in an impl my class, self is my class. For doing the fields or doing the getter methods, one of the big things is this pointer in C++, which we can easily forget about, and how to control its type. So in C++, if you have, I'm going to go back to here. In C++, if you have no arguments on the third line, because I haven't planned this order, you get a mutable you get a mutable this pointer. And to do the same in Rust, you have to do a mutable reference to self. In C++, if you want to have a const this pointer, you have to do const after the function declaration. In Rust, you just have a constant reference to self. If you don't want a this pointer, in C++, you have to annotate it static. In Rust, you just don't put a self. And if you want to pass by value, in C++, there's no way to do that because it doesn't really make sense within C++'s type system. And in Rust, you just pass by self. You just pass a self. So putting that into the getter methods, we have the getting the name by copy, because efficiency. And so to do that, you have a function that takes a reference to self and returns a string. And in Rust, you also don't implicitly have this arrow getting types. You have to explicitly write self. So here we have self.name, and then to get the value of a string instead of a return by reference, you have to clone explicitly. And then data has some bounds checking stuff that I'm not going to go over, and a clone. And then the length is also predictable, but all of these have the self dot at the start. So comparing that, generally the Rust has a bit more code here, but it also has all of the explicit clones, which is kind of a trade-off. Do you want to be implicitly allocating vectors of strings everywhere? And then using this, again, we see the ability of C++ to do allocating strings quite implicitly. So we create a vector of strings using an initializer list, and then pass that to my class, to the constructor of my class, and then we just print the name, data element 1, and the size, and that prints what we would expect. I'm using println just because it looks like the Rust code. And then on the Rust side, we have allocating a vector of strings using the vec macro, which is the standard syntax which is a standard macro for generating vectors. And we have, but you'll note that we also have to explicitly convert the string slices, which basically take the role of both string view and const char star in Rust, to owned strings. So it's slightly more explicit again. And also notice that in the call to new, we have to take a reference to both name and data. It doesn't implicitly take references, which is slightly more explicit, but also in C++, you can have the case of accidentally passing mutable references and getting weird behavior out for mysterious reasons. And then calling it, and then calling the getters looks essentially the same, even down to the std format printing. Traits are one of the big features in Rust that isn't super analogous to many C++ concepts. But it effectively defines an interface that can be implemented for a struct, for a type. So here I've got a trait of shape, and then this is saying that anything that implements shape needs to implement a function that takes a reference to itself and return an F64, which is C++ double, to get the area. And then using that, we can have a struct circle with a radius and implement shape for circle. You need to do impl shape for type instead of just impl type. And then within that, you have to define all of the functions that the trait says. So get area, and then there's the formula for a circle. I found out recently that C++20 added pi. And rectangle, the same again, just width times height is getting the area of a rectangle, width and height. And then calling these get area functions, we could make a rectangle using an initializer list and a circle. And it prints the areas as you would expect, 20 and pi. You can also call traits dynamically. So you can create a dynamic reference to a trait object. And this is kind of interesting because the dynamic reference is actually a fat pointer containing both the pointer to the v table and the pointer to the data, where in C++, obviously, if you have a v table, it's the first object in your struct or in your class. So that's an interesting trade-off of, do you want to be carrying around 2 pointers when you're doing dynamic dispatch, or do you want to be paying for dynamic dispatch if you're maybe not using it, which can also be a case. And so here is a function that just gets the area of some shape and prints it. And then we can call dynamic call at the bottom with just passing a reference to the rectangle, a reference to the circle, and it prints exactly what you would expect, the same again. The generics also use traits and are potentially more powerful when using traits. Rust generally uses a lot of generics. So here we have taking some type T that implements the shape interface, or the shape trait, and then the function takes genshape, which is a reference to said T. It calls getArea on it, and it returns the mystery shape, and it gets the area, and then it prints it. And again, switching to generic call, that works. Big note for generics is they are like templates, so they generate more code, and each of rectangle and circle here has its own implementation of generic call that is being inferred by the type being passed to it. Traits can also have associated types. So here I've added that the shape needs to have some sort of an inner type and a function to get the inner type. So what I'm meaning by this, just for a slide example, is that if you have a circle, I'm defining the inner type to be rectangle, and make inner returns a square with the size that it's the largest square that fits within the circle. And for circle, or for rectangle, I implement that the inner type is a circle, and that it always returns the circle that is the largest circle that fits within the rectangle. And then we can just have an example of calling this. This is potentially too long of an example for a slide, but it goes back and forth. It creates a rectangle and prints the area, and then it gets the inner circle of that and prints the area, and then it gets the next rectangle and prints the area for a few times, and we can see it goes down 20, 2 tau, 8 tau, so on. And you can also, you can't really use dynamic dispatch super well with trait types. You would need to have the type specified because it can't just magically get it to work. But for generics, you can also, here I've got a recursive generic call function that takes a shape and recursively calls make inner and generic call on the inner type, and that will do the same thing going down as the previous slide. I was going to have a thing on RAII, or predictable destructors. It basically works the same as C++. There's some slight caveats for the underscore operator, but that's it, and for move. But also, with no constructors, how do we have copy constructors and how do we have destructors? So copy constructors are generally implemented through the clone trait, which is just a trait that says you need to have a function clone that takes a reference to self and returns self. And destructors are called drop and are implemented by the drop trait that takes a mutable reference to self and does something with it. that you want. And also all of the members within your struct or enum or whatever you're dropping also get dropped afterwards, the same as they do in C++. One of the big things in Rust, C++ doesn't have reflection in 26, right? It's getting there. I haven't looked at C++ 26 features. So one of the big things that Rust has is not reflection. It kind of mimics reflection, but it's this derive macro that I've annotated at the top of Phil's struct, or the struct for Phil's class, which in this case it is implementing a bunch of standard traits. And these technically aren't traits themselves, they're macro implementations. But they read the type of my class, they read the body of the code of my class, and they generate you an implementation of debug, so debug formatting, which is really nice. They generate you a clone implementation, so it just copies the string, copies the vector. It can generate you a hash if you're wanting to use hash maps. It can generate you ordering if you want to have sequencing, and it can generate equality and various other things. So just to highlight the debug example, if I generate the same instance of my class as we had before, then and then use a debug formatter. One thing to note that I didn't bring up before in Rust is that you can actually put the type name inside the curly brackets. So if I didn't have the colon question mark, it would be using the normal formatter. Debug formatter, if you put colon question mark, prints using the debug trait instead of the display trait. And here it just because we have the derived debug above the struct, it can print out all of the fields of the struct using the default formatting, which would be a lot more code in C++. Also, you can have hashtag question mark for pretty printing. So this is the same thing again, but just spaced over multiple lines if you don't want it in just one flat block or one straight line. One of the big powerful ones is that, or one of the other really powerful things about this is that it can be used by the ecosystem. So non-standard traits such as SERDES serialize and deserialize, which is what SERDE stands for, just by adding SERDE to your dependencies, which I've got on the left, and adding SERDE JSON. So this is a very common trait for doing JSON stuff in Rust, and annotating the struct my class with serialize and deserialize. We can take the same code printing as before that just prints my class using the debug trait, and then we can use SERDE JSON to string to convert that class to a string, and then print that string as a JSON string. And then we can also do SERDE JSON from string to convert from the string that it just generated back to the struct. And running that, it prints the exact same struct on the top and bottom, and it also prints the JSON intermediate that it generated in the middle, which it would take a huge amount of C++, or relatively huge amount compared to the 3 lines here of C++ code to do that with any competent JSON library that I've seen. So that's one of the really big features that would be nice to see in C++, and maybe it could do even better with proper reflection, but we'll have to see. How am I doing for time? Was that 4 minutes? 10. Okay. I'll go into enums then. So enums are another really big Rust thing, and C++ kind of tried with std variant. It tried its hardest, and std optional. So it's kind of more, I've heard it often referred to as tagged unions because enums mean something very different in C++. And these are generally, especially, and so the way that these work is that we have an enum, we can define an enum type that is for example, here, implementing a similar case to the my shape from before is either a circle or a rectangle. And the circle has a single associated F64, and the rectangle has two F64s. If you want to have more expression within the types, there is ways to name these, but I would often recommend, if you have larger objects and more complex objects in your enums, just have a struct for each line, which is similar to what std variant requires. That is a small slide. And so to access the fields within an enum, we can construct using my shape : circle and one float, or my shape : rectangle and two floats. So we construct a my circle and a my square. Square is not square. And we can match, and then we need to use some sort of pattern matching to guarantee that we're accessing the correct fields. So match is the easiest one, but a number of structures have various forms of this, various forms of pattern matching they can do. And so if it's a circle, we take the radius and print it. And if it's a rect, we take the width and height and print them. And then I just do the same thing again for the square at the bottom. And it's covered up on my screen, but it does print 3 and 8 and 5. And to condense that down, you can also call impl on enums. So you can implement methods against enums. And so this is a function that just takes an enum by const reference, or takes our shape by const reference, and if it's a circle, it prints the radius. If it's a rectangle, it prints the dimensions. And then we just call identify on our enums from before. And that just prints 3, 8, and 5 as you would expect. Common enums in Rust APIs that you can't avoid because they're used everywhere for error handling is that is option, which is templated on a T. So it's either some T or it's none if you didn't have an object. And result for you successfully did something and have a T, or something went wrong and you have an E that's an error. And these are relatively analogous to C++'s std optional from C++17 and the new C++23 std expected. Going into a quick example, hopefully quick, I've got a C++ program here that opens a file that doesn't exist, and then it constructs a string, pipes the data from the file into the string, and then it prints the string. So if the file doesn't exist, what does this do? Some audience interaction. Raise your hand if you think that it throws an exception. About 10 people. Raise your hand if you think it's an invisible UB landmine. A few people. And raise your hand if you think that it just silently prints an empty string. A few more people. The correct answer is it silently prints an empty string. So there are flags that you're supposed to check if you want this to not happen. I'm not going to go into that. But what does this look like in Rust? So in Rust, we open the file, but the file open returns a result that is either a file or an IO error. So you have to match that. And in the case we have an error here, I'm just going to panic terminating the program with a message error opening file. And in the case we have a file, we want to try to read the string from the file. This has a similar API taking the string by mutable reference to write to, and it returns a result of either the number of bytes written or an IO error again. So matching that, we either print the data that we got out of this file, or we panic terminating the thread. Now, and that, when the file doesn't exist, unsurprisingly prints that there was an error opening the file. But this is quite verbose, and it's quite ugly having the nested matches. So I said before that statements return values in Rust. So actually we can have a match statement at the top opening the file. In the case of a file, it has a value of the file. And in the case of an error, it panics terminating the thread, and the type system knows that that doesn't happen. So the entire value of the match is a file. And then we assign that to a mutable file at the top in the outer scope. And then continuing down, we construct our data and read our string and then print it if it existed, or if the file had unreadable content for whatever reason, we can terminate again. But also those panics terminating are quite bad, because maybe the caller would prefer to do something and recover in the case of an error instead of just terminating. So normally you would have a function that can fail, return a result of some type or an error, and here everything in here returns an IO error. So just return an IO error. And both of those we now match the error as we match the error as E and return error E. And at the bottom, we return the unit type, which is basically a void. And we need to handle that in the outer scope, and we just print the error. But also, this is a really common pattern in Rust, to want to just throw the error up the stack and continue with the successful value. So Rust also adds an operator to do this for you, which is operator for the first match particularly. So if you want to throw whatever error you had up the stack, or just take the successful value, we can use the question mark. And now if we had an error opening the file, we throw it up the stack. Otherwise, we have a file and continue down. And then we try and read the string data. And if we have an error, we throw it up the stack. And otherwise, we continue and we print the file data. And then we return an OK. And comparing this to the C++ code I started with, this looks pretty much line for line the same, the only difference being the OK, the returning OK at the end, and the question marks on the end of the lines, which is quite nice considering the Rust has basically all the error handling you want in such a function. And the C++, we had 3 different answers across the room on what it did. So yes, thanks for listening. I'm not going to go into it.
We have time for questions. If you'll
take
questions,
I can do questions.
The question.
Yeah. Does anyone have any questions?
If there's lots of nice little conveniences, like the question mark operator, you could wave your magic wand and pull one of them into plus.
Definitely the procedural macros, or some sort of good reflection, because like proper reflection would be even better. But the ability for, if I go up, what this is actually doing is like each of these is calling a macro is calling some Rust code within that is compiled and then loaded into the constructor. That is a function that takes the token stream of this struct definition and then returns a token stream that is the implementation of the macro. So you can do basically whatever you want in there. There's some safety concerns about that, as in like you're running arbitrary code at compile time. So some better ways of that. And also you don't have access to anything outside the macro because it hasn't done generating all the types in the compiler at this point. But like something to be equivalent to this would be massive. Do you also have a question? Oh, sorry, I forgot the question. I forgot to repeat the question. Was there anything else if I could wave my magic wand, was there anything I could add to C++ from this? So.
Yeah, so first of all, thank you for that. I don't need Rust, so pretty interesting. Meaning to learn about it for ages. So you said there's no constructors and destructors.
Not as a language feature.
So when you have the
drop is a destructor, I would say.
So when you have the question mark, throw this up. How do you do resource?
The drop is automatically called as a destructor, but you don't have constructors. Phil?
So when you're doing Rust, any features from C++?
Is there anything big? I don't know about from C++, but one of the things, I mean, I run release mode because runtimes generally for even when I'm debugging, but one of the weird things in Rust is the fact that by default, integer overflows and underflows panic in debug builds, and they don't panic in release builds, which can be annoying. There's also a few things of, because Rust by default, everything goes on the stack and then gets moved to the heap, and the compiler, when optimizing, just constructs things on the heap because the move is very easy for it to optimize. You get some cases where if you create an object that's like 10 megabytes, it works in release mode because it just allocates the memory and puts it on the heap, but then it doesn't work in debug mode because it tries to put that on the stack and you blow your stack. Yes?
I've done the trait.
Yes.
And concepts.
So wanting to have trait constraints and concepts in C++, I haven't looked into. They're kind of analogous, but not, I wouldn't say they're fully there, and they're not as elegant. Which seems to be a trend of the C++ library features that get added.
Maybe just to say a bit more about that. Concepts are the closest thing. But C++ is concepts that we didn't get taken out. We're actually much closer to.
Okay. So Phil's saying that C++ OX almost had closer concepts, but didn't.
Any other questions?
No?
In that case, thank you to Joseph.
No. Thank you very much for having me.